Hi guys, thank you very much for coming out on this cold, dark, wet winter's night. Hi everyone on YouTube, hello. So let's get going. So Christmas Day, we all held our breath. It's the most advanced and complex, one-off, advanced space telescope, James Webb Space Telescope, got launched into space. There was only one of them, there was no redundancy. So we held our breath, but it got launched successfully. It spent the next month heading out to its destiny in deep space, point called L2, which we'll talk about. And then it spent that month while travelling there unfolding itself. It was so large, it couldn't fit fully assembled in a side of rocket, so it had to be all folded up. So it unfolded itself. And then the next 5 months, sitting out at that point in space, L2, it spent that time cooling itself down and calibrating its instruments and getting ready for the real science. And then, yay, last month NASA released a series of its first images to, just everyone found absolutely stunning. That's cool. And if you were one of many people thinking, wow, what's so special about the James Webb Space Telescope? Everyone's talking and, hey, these pictures look pretty stunning, but tell us a little bit more about them. And if you're one of those people, then you're in luck, because tonight's talk is called the James Webb Space Telescope, an extremely powerful infrared telescope, casting or providing a gateway to a golden era in astronomy. And tonight's going to be an introduction to the Space Telescope, a little bit about it, and then we're going to delve in and look at the first 5 images that have been released. So I've split the talk or broken it down to 2 main things we want to get to the crux of. What makes it an extremely powerful infrared telescope, and how is it providing a gateway to a golden era in astronomy? So let's start here. Why is it extremely powerful, and why is it in the infrared? Let's have a look. Now, that there is a full-scale model, mock-up of the James Webb Space Telescope on the front lawn of NASA's Goddard Space Flight Center, where it was mainly assembled. Check that out. I haven't counted them, but I estimate there's about 400 people in that photograph. Can't see any wallies in there, any reds or white stripes. If you can, let me know. But yeah, about 400 people. So that gives you an idea of the sheer scale of it. In particular, what makes it so powerful is this mirror, 6.5 meters across. That's half of this room. Holy moly. So look at the size of it, and I'm going to show you a better picture shortly. But it's the primary mirror, the size of the mirror, that gives any telescope its grunt, if you will. How many particles of light or photons can it capture and then focus down with its mirrors towards the instruments? That's what it's all about. A big mirror means more powerful telescope, which means you can see fainter objects, whether they be further away, whether they be smaller, but you can certainly pick up fainter objects, make them brighter, and it brings out more sensitivity or more detail, resolution, if you will, of images. Just you see more detail, better resolution. That's it there, the mirror. Here's the technicians down here. Look at the sheer size of that beast. To give you an idea, Hubble, which everyone made a big hoo-ha about when it was launched in 1990, that was 2.4 meters across. This is 6.5 meters across, and that is what makes it so powerful. So I mentioned the word infrared. Why measure in the infrared? So first of all, let's have a little bit of introduction, a little bit of a review, if you will, of light waves. Light waves, also known as electromagnetic radiation, which is waves of electric signal and then magnetic and then electrical and so on, and alternating between electric and magnetic waves. That's what's called the electromagnetic radiation. And it comes in quite a wide spectrum. What we see, what our own eyes or retina are sensitive to, is just this small little bit in the middle here, from 400 to 700 nanometers, what they call the visible part of the spectrum, tiny. And that's what refers to the wavelengths. When we talk about wavelengths, sort of 400 nanometers up here and 700, they're referring to the wavelengths of the light here. And as the wavelength gets shorter and shorter, the photons get more and more energetic, and you start getting into ultraviolet light, then X-rays, and then the most energetic of the lot, your gamma rays. Going the opposite direction, you've got your infrared wavelengths are starting to get longer, and you're starting to get lower energy photons. You're going to the infrared up to about 1 millimeter, and then microwave up to 1 meter, and then you've got your radio waves. So that's sort of a bit of a review of light. It's this bit here, the infrared, that we're interested in tonight, that James Webb looks at. And the wavelength varies from 700 nanometers, and let's stick in microns. I think for the rest of the talk it's going to be a lot easier. 0.7 microns up to 1,000 microns, where you start getting into microwave wavelengths. So that's what we're interested in. It's then split further into 3 segments or regions, if you will: the near infrared, the mid infrared, and then the far infrared. And these splits here are about 5 microns. So 0.7 to 5 is known as the near infrared region. 5 microns to 40 microns is known as the mid infrared region. And from 40 microns up to 1,000 microns, or 1 millimeter, is the far infrared. So that little diagram will be very useful. Keep that in your mind for tonight. Now, there's 2 important properties. You're probably thinking, yeah, I get that, but tell me some more, get to it. Well, what are we doing in infrared? So one of the big things about infrared, it penetrates cold dust and detects glow from warm dust. So essentially normal thick dust that you can't see through, in particular the near infrared, just cuts straight through it, and you'll see that shortly. So that's a big plus about infrared light. And the other thing to mention here is infrared light is absorbed by the atmosphere. You might think, why are they putting this big thing up in space? Earth's atmosphere absorbs a lot of the infrared wavelengths of light coming from outer space. In particular, the carbon dioxide, and particularly more so, water vapor in our atmospheres. That's why the big telescopes that on land-based ones are way up high in the mountains, the Atacama Desert or Mauna Kea and so on. They dip their toe, they just delve a little bit into the near infrared, but they do that by getting above 90% of the atmospheric water vapor, so they can start seeing some of the infrared. But if you really want to do it properly, you've got to get above the atmosphere, hence space-based telescope. Now, there's 2 key things that make it more sensitive and capable of infrared observations. That's the location of it and the design features of the telescope. And I mentioned location briefly, but this is a point L2, and it's 1.5 million kilometers that way. So here's a diagram here of the sun and the Earth and the moon. Whenever you get sort of a system like this, where you get a star, so it's the sun, and then something orbiting it like the Earth, you get points of gravitational stability where things are reasonably stable there, and they're called Lagrange points, after a famous French guy, Lagrange. And there's 1 there, 2, 3, 4, 5. These are at 60 degrees. The talk's not about those, so let's move on from there. So it's gone out to a nice gravitationally stable area L2, where to stay there it requires a minimal amount of fuel because it's a nice gravitationally stable area. And you might think, oh, L2, why not L1, L4, L3, L5? L2 is the best of the lot. 1, because in one sweep you can just look away and block out the heat and the light from the sun and from the Earth. And that's what that sun shield is all about, which we'll talk about now. But that's why it is. So it's 1.5 million kilometers out that way. And that's what took a month to get out there. So, which brings us, to some of the design features, and we're starting off, here's that big sunshade. Woohoo! That, my friends, is the size of a tennis court. 5 layers, down there. It's made of Kapton, which is a thermoplastic, which tolerates extreme temperatures, extreme cold, extreme heat, and so on. So, size of a tennis court, 5 layers of modern thermoplastics. Look at the size against the technicians there. So that's a key design feature. The other one is the mirror coating. The mirror is coated in gold, not just to look flash and justify a big price tag, to be a bit of bling in the space, but we traditionally use silver and various things for reflectors and mirrors and so on Earth with visible wavelengths of light. Infrared reflects most optimally against gold. Gold is your best material to reflect that infrared wavelength of light. So it's made of gold. It's also very stable. Gold is very stable against corrosive forces, corrosive factors in outer space. So it's very stable, and it's the ideal element for reflecting infrared wavelengths of light. And it's a nice bit of bling in space. How about the instruments? So the sunshade is protected against heat and light. You've got that lovely large gold-coated mirror now that's capturing the light and focusing them down towards the instruments and then the detectors. So let's have a closer look at these. So there's 4 main instruments on the James Webb. 3 are looking in the near infrared. So the near infrared range is the 0.7 to 5 microns. Mid-infrared, the James Webb goes out to 25. Why? That's all it needs to go out to do what it has to do. And every time you try and push science and technology, it comes at an extra cost and so on. So they do a lot between 5 and 25 in the mid-infrared. So there's 3 instruments that observe in the near infrared called the NIRCam, the NIRSpec, and the NIRISS. We're going to look at all these individually shortly, and MIRI for the mid-infrared wavelength. They're all packaged. This sits behind the mirror, the instrument. So let's just go back. Here's your mirror here, and it's just out of sight, but behind here is your instrument setup. And that's it here. The instrument frame, they call it, and all the instruments sit in there behind the primary mirror. So let's go and have a look. Let's take the hood off, shall we, and have a closer look. So here's NIRCam. It's the telescope's primary and most sensitive imager by a country mile. It can see out faint objects out to a magnitude of 29. To give an idea of magnitudes, the higher the number is the fainter the object. So the sun's very bright, for example, that's minus about 26 or so. But as you get to 0, it gets dimmer, and then you start getting fainter logarithmically. So that's real faint. With unaided eye, we can see 6, 6.5, something like that, depending how good your eyesight is. So it's logarithmic. The Hubble sees out to about magnitude of 22. So that's a factor of 7 difference. It's logarithmic. That means the James Webb can see something 129th as faint as what the Hubble can see at its limits. So something 120 times more faint it can see. It's mind-blowing. It has 29 filters, and you probably all are familiar that these professional telescopes have a big filter wheel where they can, each filter is designed to let a certain wavelength of light in, or colour if you will, and it rotates around, and it's a big wheel they can spin around in front of the instrument. And most of us are used to 5 and 6 different colours on a filter wheel. This baby's got 29 filter wheels. Oh, I was going to put a picture diagram up there or a photograph of it, but I thought I wouldn't be able to control myself. It just looks gorgeous. 29 filters on its wheel. It's got a coronagram. And you might say, well, what's a coronagraph? Or a coronagram? And essentially, it's a physical shield that's on the filter wheel. Physical shield that shields or blocks out the glare from something bright, such as a star, that's blocking you out from seeing something close by but a lot dimmer. And here is a perfect example. Here's a bright star with an exoplanet. And they've put a coronagram, they've lined it up here so it's blocking out the glare from this bright host star, and now you can see the exoplanet. They use it to study the sun. They call it a coronagram, for the solar coronagram, to look at the atmosphere of the sun, just block it out. So that's what a coronagraph is. It's also, which we're going to talk a little bit more detail shortly, it's got a wide field slitless spectrograph on it, and we'll talk about spectrographs now. Because NIRSpec stands for, it's a multi-object spectrograph. And just briefly, a spectroscopy involves either a prism or a grating, or you can get a combination of the two called a grism. And you get light, whether it be from stars or galaxies. It enters the instrument to the spectrogram, and it splits the light up into its various wavelengths like that. Just like water droplets create a rainbow, and we've all done the prism thing. Your Pink Floyd t-shirt, all the same principle. And what the information, so that's a whole separate talk, but needless to say, splitting light up into its various wavelengths gives you a lot of information on how far away a galaxy is receding from you, or a star, and straight away towards you or away from you. That in turn, you can calculate its distance if it's far away. It tells you the composition, what sort of elements and what sort of energy states they're in. That's the sort of stuff you tell. And you can tell the temperature of an object. So a lot of information comes from a spectrograph. Now, the interesting thing, they call it a multi-object spectrograph. I bet you're thinking that's interesting. It's because it's got this little baby, a micro shutter array, where it's got to see, it can see up to 100 different galaxies, individual galaxies, all simultaneously, all at the same time, and splitting their spectra up, because it's got this array of micro shutters, 250,000 of them. Look, they're little microscopic. Each one is the size of a small bundle of human hairs, and there's 250,000, they're all in an array. And if they see an object, let's keep things simple, say over here, and an object here, another one here, they just open up the relevant shutters so they can point part of the spectrograph here, part of it here, this galaxy or star over here. They can do that 100 times over in one exposure. Amazing, and it's pretty accurate. Comes in low, medium or high resolution, so that's another big plus. There are reasons you want to go to low, high and medium resolution, so it's pretty versatile. So that's just, that instrument is totally dedicated towards spectroscopy in the near infrared wavelength range. NIRISS. NIRISS is the Near Infrared Imager and Slitless Spectroscope. So as the name implies, it's an imager and a spectrograph. So the imager uses what they call aperture masking interferometry, whereby they get a series of holes within the filter, in the field, get various views, and then they combine those views together to increase the resolution. It's a process called interferometry. It involves computers and so on. They use it a lot on a grander scale on Earth with telescopes. Your Event Horizon telescope, same principle. So you get various views of things, combine them together to give it much better resolution. And they use that in particular for viewing, they hope to view exoplanets directly. Most of the exoplanet discoveries and analysis up to date has all been through indirect measurements. You can't actually look at the exoplanet itself. This is going to increase the capability of doing that untold. Slitless spectrograph. Okay, we've talked about what a spectrograph is, but what's all this slitless business? Your near spec, and most spectrographs have a tiny little slit in them, so they just allow a slither of light through, so they can focus on just a very, very narrow beam of light and create a high resolution image of that. So slitless is when they don't have that slit, so they open up to the full field and get light, all the light from all the objects that are in your field of view. It's quite useful for wide field, taking wide field views, whether you're taking a single object spectroscopy or multiple objects at once. It's very good if you've got a wide field of sparsely populated galaxies or something like that. One over here and one over there and one over there. And in particular, if they are faint. Slitless means you're allowing more light in, which means you're able to see fainter objects. And that's one of the big pluses. So it's low resolution, because one question people have to say, well, why bother with low resolution when you can just have high the whole way? Well, the reason being is it's like a lot of things in life. It's a trade-off. And your high resolution, you've got to have a small slit, which means less light, which means you only tend to looking at the brighter objects. If you get something really faint, go to slitless, low resolution, but you can brighten up the image because you're getting all the light of that object. So it's really great when you get a sparsely populated wide field with a lot of faint galaxies. They'll use it for that. And then MIRI, the mid-infrared imager. That's actually an image, despite its name, it's actually an imager and a spectrograph. So that's two that are just dedicated to the mid-infrared wavelength range. Both the imager and the spectrograph have coronagraphs that they can blot out with a shield that bright object so they can see something fainter to one side. It comes in a slit or a slitless mode. The slitless mode on MIRI is very useful for doing time series observations, and your classical example of that is you wanting to analyse the atmosphere of an exoplanet quietly transiting in front of its host star, and that's going to might take 2 or 3 hours to do that, and you can just sit there with that slitless function. It's MIRI because it's a lot of the chemicals and compounds that you're wanting to analyse. They show up in the mid-infrared, so that's why you're using MIRI, and they'll often use the slitless for that. So instead of that little narrow light, you suddenly got a much wider field to look at and monitor that spectrum as it goes across. So those are your 4 instruments, 3 for the near-infrared, 1 for the mid. That just sort of gives you an overview. Okay, so as I mentioned, the mirror is designed to catch the photons, focus them down. The instruments are there and the filters to filter out. So you just allow the particular wavelengths you want through. The instruments do their thing, whether it be imaging, whether it be spectrographs, but you need a detector to pick up these photons of light and register them and give electrical signal for them. And the detectors really are state of the art. They didn't just go down to JCAR and get themselves some semiconductors and use those. These are very specific and very sensitive to infrared photons. And I know a lot of you perhaps will, with your observing, are familiar with the whole concept of using silicon for a semiconductor for your CCD imaging. Silicon is readily available, it's really affordable, and it does the job quite nicely for visual wavelength light. Infrared, it doesn't cut the mustard. It can't efficiently detect those infrared photons and the sensitivity that you really want. So for that reason, the near infrared has 15 detectors, and it's a mixture of mercury, cadmium, and telluride based. They operate at about 37 degrees Kelvin, or minus 236 degrees Celsius, almost as cold as student flat in Dunedin in the wintertime. That's pretty chilly, huh? I'm going to talk about the cryogenics shortly, but the telescope, just because of its design features, without any cryogenics, comfortably gets down to those temperatures. Pretty amazing, isn't it? That's pretty chilly up there, and that's just because of the sunshade, the design of it, and so on, and its location. The MIRI detectors for the mid-infrared, there's 3 detectors, and they are the silicon-based with arsenic being doped in with it, and that combination works quite nicely for a good sensitivity to infrared light in that 5 to 25 micron range. Here's the catch. It ideally operates in temperatures below 7 degrees Kelvin. So, 7 degrees Kelvin, 0 degrees is when everything sits still, nothing sits still, everything, we're all jiggling. Everything in this universe is having a party. It's jiggling all the time. It's generating heat. Minus 7 is so close to absolute 0. That's amazing. I converted it for you. Minus 266 degrees Celsius. Whoa. That's what you need cryogenics for. And here it is here. That's it here. So basically, yeah, it's a sophisticated refrigerator. All its parts are distributed all around just to fit in the little gaps. It doesn't have to be in one slot. So space is at a premium. So it slots areas in there. So it's spread out throughout the whole instrument bay or instrument frame. They've assembled it here for testing it in vacuum chamber. But it's helium gas they use, and it brings the MIRI instruments down, or the detectors rather, down to about 6 degrees Kelvin. And they work quite comfortably with that, so it can bring it down to 6 degrees. It works at about 6.2 degrees, so well below its 7 degrees threshold. It's one heck of a refrigerator, isn't it? Okay, so we know it's powerful. We know it works in the infrared wavelengths. We now know why it's powerful, why it can detect things very sensitively in infrared. How about why infrared? Why infrared? And the bottom line is, looking at the infrared, you can uncover a lot of other things in the universe. And so these 3 instruments here that observe in the near-infrared observation. As I've mentioned, dust is largely transparent. You can cut through. You know, we all get frustrated trying to look at something and a big cloud of dust comes along and covers it up. You can't see it. Looking in the near-infrared, you can slice through it and see things glowing. Your cooler red stars glow a lot in the infrared, predominantly in the infrared. Your protostars become visible. Protostars, by definition, and we're going to talk about this too, stars form big clouds of gas and dust, start collapsing in themselves, their own self-gravity, collapsing in. You've got a big ball of cloud. Right at the core of that big ball of dust, gas and dust, it starts, the centre core starts collapsing more and more, and you start getting nuclear fusion kicking in, it starts glowing. Anything that's still enshrouded with dust that you can't see under visual wavelengths is by definition called a protostar. You can't see, you know it's there, but you can't see what's going on. It's glowing in infrared and it's enshrouded with dust, but we can't, with our eyes, visual wavelengths can't cut through that dust. So suddenly you'll be able to see protostars that are these young stars glowing very dimly, infrared wavelengths enshrouded with dust. The interstellar medium, monocles, in other words, that's the monocles that hang out in space between stars and galaxies, in particular, a very important bunch that are very bright at about 3.3 microns, called the polycyclic aromatic hydrocarbons, and they are a series of compounds containing carbon and hydrogen. We have them on Earth in terms of soot and stuff. They are thought to be very, very important in the formation of stars and, of course, planets and life. The universe, they're just ubiquitous. They're everywhere throughout the universe. About 20% of the carbon in the universe is thought possibly being tied up in these chemicals, and they show up quite nicely. There's various species of them, and there seems to be quite a glow at about 3.3 microns of these polycyclic aromatic hydrocarbons. With MIRI in the mid-infrared, I mentioned in near-infrared you can see through dust. Dust, like everything else, absorbs energy and then starts to emit energy. And if you get really cold dusk on its own, really, really cold and still, that emits in the far infrared. But if you've got stars nearby, they're emitting visual wavelength light and ultraviolet light, the dust will quite happily absorb that and then will glow itself in mid-infrared wavelengths. So you can have a look and see where a lot of dust is in mid-infrared wavelengths that you can't see visually. I mentioned protostars. Also, you get disks around as the stars start collapse. The disk, rather the cloud rather of gas and dust starts collapsing into itself. It's rotating faster and faster. Centrifugal forces creates a nice little disk out there, and that disk eventually, hopefully, forms into planets. They call it a protoplanetary disk. They glow. Those protoplanetary disks and protoplanets glow quite nicely in the mid-infrared wavelength. So that's the importance of MIRI on board. And once again, a lot of the polycyclic aromatic hydrocarbons glow in there. Saw an interview with some of the NASA guys, the guy in charge of MIRI, and he said he had to argue with NASA for about 5 years. Why don't we put a mid-infrared instrument on the telescope? And it took him 5 years to convince NASA. Maybe that's a good idea. So there you go, yeah. But it certainly is very, very powerful addition. I put this up here. This is a Hubble, couple of Hubble pictures, but it illustrates that concept beautifully. This is the Pillars of Creation, came out about mid-90s, publicised by NASA, got a lot of attention. It was part of the Eagle Nebula M16, and you see these big fingers, if you will, of thick gas and dust here. This is visual wavelengths, and you see all these stars around it and so on, but you can't see much through here. Suddenly, just changing to infrared wavelengths, looking at infrared, you know, the dust is hardly there. You can just almost see straight through the dust. And look, suddenly all these hundreds of stars become visible. All this was enshrouded with dust. All these little protostars in here, covered in dust. You can't see them optically because it can't get through the dust, but also they're glowing predominantly in infrared anyway, and that's what you're seeing, but it's cutting through the dust. So it's a Hubble picture, it's an oldie, but I think it's a goodie that illustrates the principle of cutting through dusk. Okay, so we've talked about what makes the James Webb an extremely powerful and infrared telescope. How is it providing this gateway to a golden era in astronomy? Let me convince you. So, main thing that astronomers are interested in a lot of things, but I've just picked out 5 frequent things they're interested in, and which are best illustrated through these first 5 images. They illustrate these quite nicely. So we're going to talk about how stars like our sun die, how stars and planets form, how galaxies merge and interact with one another. We'll talk about the very first stars and galaxies that got up and running in the universe, and then we'll look for signatures of life in the atmospheres of these exoplanets. Exoplanets, of course, being planets outside our solar system. So let's get underway. We're going to do a tour. This is our galaxy here, and that's the disk of the galaxy, and that's all those gas and dust, in particular thick dust lanes through here. Look how thick it is, and that blocks our view a lot. Our galaxy is 100,000 light years across. 1 light year being the distance that light travels in a year, which at 300,000 kilometers per second, in 1 year light travels 10 million kilometers. 1 light year. That's 100,000 across, 100,000 light years. So that's our galaxy. That's looking across the plane of the disk of the galaxy. See the nice big bright, super dense, super bright bulge in the middle there, and then you're getting out into the suburbs. We live about here, about 26,000 light years out from the middle, halfway up. Some days when I turn the news on, I'd rather wish we lived over here, but anyway, but we don't. So that's us here, about 26,000 light years out. We're slightly above the plane, the absolute plane middle of the disk of the galaxy. And we're going to start our tour. We're going to go to our closest object, the southern ring, a planetary nebula that's 2,000 light years away within our galaxy. And then we'll come home, and then we'll head down here to the Karina Nebula, which is a nice big star formation region, 7,500 light years away. And then we'll head out of the galaxy, and we're going to look over here and look at Stephan's quintet, 5 galaxies, 4 of which are 300 million light years away. We've moved well and truly out of the galaxy. We're no longer talking about thousands of light years, we're talking millions of light years. We're then going to jump over here and look way, way back into the space, about 3.6 billion years look back time. In other words, when the universe was about 200 million years old. We're going to go right back here and look at SMACS 0723, and then we'll finish up and we're going to look at the atmosphere of an exoplanet, WASP 96b. So that's our little journey we're going to do. And we're going to start looking at all these. And I thought I'd put in here a good way to approach these 5 separate images. With each image, I'll talk about what it is you're looking at, with what instrument you're looking at, and a little bit about that type of object. Then we'll talk about what sort of details you can see in the photograph, some interesting details, and then we'll talk about what features in that image astronomers are interested in that are going to help them in the future to study in more depth and help them understand the structure of the object or the astrophysical processes going on. So let's do it. So this here, which is so nice to see on the big screen, isn't it? This is the Southern Ring Nebula, an image of a planetary nebula with the NIRCam, 2,000 light years ago, as mentioned. Now, what is a planetary nebula? Nothing to do with planets, it's just a historical name. But essentially what you're looking at is the death of a star up to about 8 times the mass of our sun. And all stars spend 90% of their time sitting on what they call the main sequence, just a term, and it's a period in a star's life where it spends 90% of its time, nice stable state with burning hydrogen into helium in its core to generate energy. Stars up to 8 solar masses, solar mass being the mass of our sun, turn into, when they run out of hydrogen in the core, a series of other processes goes on and they become red giants. And one of the latter stages of a red giant is called the asymptotic giant branch, the AGB stage. And it's a very short stage, and it's whereby the star starts pulsating. It's called the Kappa mechanism. It's a I do as part of my talk on Seaford variables, but it's a mechanism in there of partial ionized zones, involve radiation, pressure, and so on. But needless to say, the star starts pulsating, and every pulsation outwards, it sheds or puffs out some of its outer layers into the space around it, the interstellar space. Then it shrinks back down again, and it puffs back out again, and puffs another big layer. It pushes it out. Eventually, it exposes its central core, a hot core of oxygen and carbon, known as a white dwarf. These are really hot, the surface temperature up to 100,000 degrees Kelvin. To give you an idea, the surface of our sun is about 5,800 degrees. The surface of these white dwarfs, these exposed cores, about 100,000 degrees. So they emit really high energetic ultraviolet photons. And that's what a planetary nebula is. Now let's have a look at the image, what you can see here. I've got the near cam one here, but I've also put Miriam here as well, just sort of smaller because it's focused. This one looks most spectacular, but I've put Miriam here to show a few points. First thing, when you look at all these James Webb pictures, you see these big bright stars here with big spikes around them. What's that all about? Those are stars in the relative foreground of the object. They're relatively close and very bright as far as the James Webb is concerned because they're so close. And because of that, the intense light is very prone to diffraction. Diffraction is just a property of light because of its wavelength, its wave properties. When it strikes a surface of an object like the edges of a telescope, or in the James Webb's case, the big struts or beams that hold up the secondary mirror, light gets a bit scattered, or what they call diffracted around the side of it, and it creates that pattern. And that's called diffraction spikes. You see them in a lot with telescopes. It's 8 spikes. You'll see 1, 2, 3, 4, 5, 6, and then 7, 8 horizontally. And that's almost, sort of typical of the James Webb, to the point of in the future, if you ever see a picture like that and you see these big bright diffraction spike stars, you almost certainly think that's a picture taken from the James Webb. No big deal. They're just very close. They don't upset the data at all, anything like that. If you want to look at something behind it, you just reorientate your telescope a little bit and look at it later on. But it just so happens one of them here is right in the middle, blocking out where the white dwarfs sit. But look at this, one of the beauties too of different wavelengths. Look in the mid-infrared, there you can see the 2 central stars. Most stars, unlike our sun, come in a partnership like a binary. You can get 2, 3, 4, 5, 6 stars, all gravitationally bound. And a lot of them are binaries, and just that's exactly what you've got here. You've got 2 stars at the center. It's the one on the left, the smaller one, that's the hot white dwarf, blazing out ultraviolet light. And the one just to the right is a main sequence A spectral class. So it's on the main sequence. It hasn't gone into the red giant phase yet. It will eventually do this in due course. Here we go here. Let's go back to the near infrared because we started looking at this one. So they're sitting there, in particular the white dwarf, blazing out high energetic ultraviolet radiation. There's a lot of gas here that's been ionized, and that's what's glowing in the near infrared. So a lot of hot gas that's been energized, that's fluorescing essentially, glowing up here. And then also there's gas spread amongst all this dust. And look at all the layers that you can see here. You can see little sort of, these are like bow shocks, if you will, going out through here. This is detail they've never seen before in these planetary nebulae. You can see dust in the middle. You can see more little sort of shock waves going through here where it's being pushed out. So that's the near infrared. Then you go to Miri, and what shows up? It's your warm dust and a lot of your chemicals, your polycyclic aromatic hydrocarbons and so on, and that's what's showing up in blue here. So the dust is showing up in red, so there's a lot of dust that doesn't show up here, but you can suddenly see it in mid-infrared, and your blue is showing up all your hydrocarbons, because the outer layers of all these stars were busy, producing carbon and carbon compounds and spilling out, and so you can start seeing this. The importance of all of this is that all this material that's going out is going to enrich the interstellar space, which is providing material for the next generation of stars and planets to form. So it makes sense. It's pretty nice to be able to understand it before that event even happens. The other interesting thing is they can look at all the different layers here, and I can count at least 8 different layers going back through here. and they're able to analyze the temperature, the composition, or a lot of the features of each of those layers. What does that represent? It represents every time there was a pulse. And every consecutive pulse of material represents deeper and deeper material within that AGB star. So it follows, if you start analysing layers of all these, of all this sort of gas and dust that's been expelled, you can start to get a better understanding of the inside of these AGB stars. And AGB stars, because it's such a relatively small period of time, you don't see in their lifespan, you don't see a lot of them. So this is a lovely opportunity. That'll sit there, all the stuff will eventually dissipate over sort of 10, 20,000 years or so, that sort of time frame. So it gives the scientists a lot of information on the enrichment of the interstellar medium, and the composition, and the process of expulsion too. They get a lot of information on. So that's the Southern Ring Nebula. So that's how stars like our sun die. How do stars and planets form? Whoa, look at this, isn't it beautiful? I'm enjoying this on the big screen too, actually. This is lovely. So what you're looking at here, this is a region where stars form, and it's just a much smaller region as part of what they call the Karina Nebula. The Karina Nebula, as you see here, 7,500 light years away, it's a massive region. You think Orion's Nebula is big, this is far, far superior. People don't talk about it because it's Southern Hemisphere and not Northern Hemisphere viewing. But it's just a small part of the Karina Nebula. And so a little bit about star formation to explain some of this. You get these huge, giant molecular clouds, these clouds of thick, dense, cold gas and dust. They're just light years across. They're massive. They're called giant molecular clouds. Something will trigger it. You either get a large region or the whole cloud. Segments of it, starts rotating, and then under its own gravity, it starts collapsing and as it rotates. And then you get increased concentrations, or knots, if you will, little denser regions that start collapsing in upon themselves. And it's those little knots that develop into individual stars. So you start getting a series of clusters of stars forming from these much larger regions of thick, dense, cold molecular monocles and gas, dust. And it makes sense that the bigger knots or balls of gas and dust that are coming down to form stars, because you've got more mass, so you've got more gravity, stronger gravity, it makes sense that the big ones are going to form into proper stars and get up and blazing a lot quicker than those small ones. And that is so. So what do we know about big stars? They get hot, and what happens when a star's hot? It starts blasting out high energy ultraviolet radiation. And that ultraviolet radiation then energizes all the rest of the gas and dust around it. Also, you get very strong, what they call stellar winds, big blasts of charged particles streaming out from these big stars as well. And this whole process does two things to the rest of the gas and dust. It causes regions of compression, which accelerates further star-making process because you start pushing things together. But on the flip side, all that high energy radiation also starts to heat things up. And stars, when they're forming, they don't like to be hot because these things start to move apart again. So on one aspect, it can promote star formation. On another aspect, it can inhibit or slow down star formation. So that's what's going on here. And behind all that dust and gas and clouds and so on, you'll find lots of protostars. So here's the cavity. Your OB stars are out of view here. They're up here. Look at all these diffraction spikes here. You know that these are stars and they're relatively close to the telescope in the foreground relative to this, and you can see them. So you just ignore those. Your big OB stars are sitting up here, but they're energizing all that high energy ultraviolet light, those big intense stellar winds, the sculpturing and create a big cavity through here. Look, all this little wisps of blue and stuff. That's hot gas that's been ionized. You can see structures here and pillars of thick, that's where you're getting thick bits of dust that are resisting the forces of the radiation and the stellar winds at this point in time. So you're getting the sculpturing going. Look at the detail in here. And suddenly you're starting to see, look, hundreds and hundreds, and look, stars. Don't everyone get too excited. But look, there's just stars everywhere. You can't see that with visible wavelengths. And these are all protostars. They're enshrouded with the dust, but suddenly you can see them. And you're probably thinking, well, why aren't we just seeing them all with it? What's all this dust here? Why are we still seeing some dust? Everything in life, nothing's 100%. Near infrared is mostly transparent to dust, but not 100%. Why? Remember, there's a big spectrum, 0.7 to 5 microns. At the shorter wavelength end, sort of closer to the 0.7s, some of that light is a lot smaller than some of the larger dust grains in the nebula. So a little bit of light, and they sort of reflect and scatter off that. So you do get a little, it's less than 5%, but you do get a little bit of reflection and scattering off some of the dust at those shorter wavelength ends of the near infrared end of the spectrum. And that's what you're seeing here. But suddenly you can make out some of all these structures that are going on here. But look at all these stars, just beautiful. In there at about 3.3 microns, you'll have your polycyclic aromatic hydrocarbons again. You'll also see when these stars, these protostars are collapsing down, they're spinning faster and faster. You've got big balls of charged particles. And what happens when you get moving charges, electrical charges, you get magnetic field lines going on. So you get all these magnetic field lines, and those magnetic field lines are twisting and distorting around and around. And in that whole process, those magnetic field lines direct the charged particles at bipolar jets, at the rotational axis poles. You start getting jets of material, hot gas and dust being fired that direction. Once again, enshrouded in dust. And that's a pretty important process in the formation of stars. And NASA has coloured them in gold. So wherever you see these little patches of gold, they are bipolar jets of materials that we wouldn't normally see. There. You look around them, there's a few of them dotted around. So they've encoded those jets in gold. So suddenly you see these protostars you can't normally see at a crucial, in a very short space. You're talking 50 to 100,000 years this process is going on before eventually the dust goes, and you've missed the ability to see this really crucial process of how stars form and how the jets operate and so on. So they'll be able to see all that. So the NASA scientists, when they calm down, they won't be excited as I am, obviously, but when they come down, what are they going to be interested in? They're going to want to study more these big O and B stars. That's the name given to these big, giant, massive stars. They're going to want to know more about the balance between compression, star formation, encouraging star formation and inhibiting it, and so on. They're going to want to study factors that determine what sort of factors in a gas cloud determine the numbers of stars that form, the types of stars, the sizes of stars that form. These are all a lot of unknown questions that hopefully they will learn. Not necessarily maybe from this image, they'll do some more detailed science. These images, of course, are just designed to illustrate the telescope works, and we can do some pretty amazing stuff in the publicly sort of designed for the public. I put this in here. This gives you an idea of scale. That's 2 light years across. So I think this is about 12 light years across. Remember, 1 light year is 10 million kilometres. So just the sheer scale of what's going on here. So how do stars form and planets? How do they die? How about these galaxies form? How do galaxies merge and interact with one another? And here we have what they call Stephan's quintet, 300 million light years away. And it's 5 galaxies that appear to be all close together. This galaxy here is actually in the foreground. That's only 40 million light years away, this galaxy here. It's just the alignment. It looks like they're all together. It's not. That's just in our line of sight. It looks very close. These are the 5 galaxies, 1, 2, 3, 4, that they're really interested. And they're in what they call a group of galaxies. You've probably heard the term clusters and groups. Galaxies come in clusters, but when you get a small number, you tend to call them a group. Like our Milky Way is part of the local group. It's just another name for a small cluster. This is a composite of 1,000 pictures. It's a combination of NIRCam and MIRI instruments, images. NIRCam, they've coded white and blue. So you see that any bits of blue and white, that's from NIRCam. And they've coded the MIRI mid-infrared wavelength signals, they've coded them to yellow and orange so you can separate them. And when galaxies are obviously driven, like anything else, by gravity, and so they have an influence on one another. So they're constantly moving around. And gravity, as you know, is an attractive force, so eventually it brings them together and galaxies will merge. They don't necessarily just poof, come together like that. because they're coming at all different glancing angles to one another and they've got their own momentum, they tend to do a little bit of a dance and a lot of interactions first, and one will interact and then you get a bit of overlap of gas and dust as one swipes one. That will slow this one down or slow that one down. They change their trajectories. They'll do a bit of a dance. They'll come back and have another swipe at one another, eventually to fully merge. And as you can imagine, when they do start interacting like they sort of overlap one another a little bit, you start getting compression of gas and dust coming together. Hello, what do you get, guys, with compression? Star formation. And that's what Miri picks up here. Look at all the star formation that's going on just through the interactions between these two galaxies getting close together. These two galaxies are almost completely merged. So the importance of this, well, first of all, look at just what else things you're looking at. There's thousands of distant galaxies. Look, these are all galaxies, thousands of them in the background, which they'll slowly pull those apart and have a closer look at them. Here's your diffraction spikes and so on. So otherwise, the importance of this is that this process would have been very common in the early universe when the universe was a lot crowded and a lot of smaller galaxies. The universe was crowded, they're all moving in. There would have been a lot of interactions going on, a lot of merging going on to create the bigger galaxies that we see today. And it makes sense. We can do all the computer models, simulations as we like, what probably happened, but you can't beat a ringside seat relatively close to it all in these infrared wavelengths to see actually what goes on when galaxies do interact and merge. And this is just beautiful for the astronomers to see. So it gives them an insight into a lot of the process that occurred in the early universe and how that universe slowly evolved, in particular how galaxies evolved. As a bonus here, I've mentioned thousands of distant galaxies. There's also an active supermassive black hole sitting right there in this galaxy. Black holes, as you know, are super dense regions of space whereby they're so compact and so dense that the escape velocity is greater than that of the speed of light, so nothing can leave them, and hence the name black holes. Most black holes that we talk of tend to be stellar black holes, you know, masses of about, say, 3, 4, 5 solar masses and so on. But at the centre of most decent-sized galaxies, including the Milky Way, there's a central supermassive black hole, and they're usually millions to billions of solar masses. The one Sagittarius A star at the middle of the Milky Way, which they recently imaged with the Event Horizon Telescope, that's, I think, about 4.2 or thereabouts million solar masses. So they sit there mostly quietly, but if some material come along, they decide, oh, lunchtime, and they start nibbling away and munching on material, gas and dust that goes by, and that creates them into that active stage where it doesn't just go like that. It tends to form a disk around it. Once again, you get magnetic field lines getting distorted and you start getting jets coming out of them. Gas and dust starts to shrouding them in a cloud. So a lot goes on when they start becoming active. And there's an active supermassive black hole here. So they didn't just go look at it and go, oh, that's interesting. What's for lunch? No, they got out their spectroscope. And this is Miri's medium resolution spectroscope, mid-infrared wavelengths. And they had a look at all the gas and dust, the big cloud that was covering and shrouding the supermassive black hole. And they're able to have a look at the constitution, what makes up the gas and dust. And they conclude there's a lot of molecular hydrogen, silicates, that's sand, and so on. Finer sand than on our beach sand here, but essentially it was hydrogen and silica, so like a lot of sand type materials that just making up that big ball of gas and dust around the supermassive black hole. You know, this is stuff that they couldn't do before. They had a look, they identified some jets coming up to the sides, the spectroscopy to have a look at the constitution of those. They saw iron, argon, neon, sulfur, and so on, oxygen. All these elements were in there. So they concluded, the outflowing hot, because they can tell not only the elements, but what sort of ionized or energized states these elements are in. That's the sort of stuff they can tell. They can also tell the velocity, how fast a lot of this material is traveling and how hot it is. So that's just as a bonus looking at Stefan's quintet. Pretty amazing, huh? It illustrates too what a powerful tool spectroscopy is. So that's galaxies merging and interacting, in other words, sort of conditions in the early universe, how galaxies came to be larger. how about the first stars and galaxies in the universe? And so just a couple of slides here, a few little principles. So the first stars and galaxies are going to be faint and they're going to be stretched into the infrared. Let me explain. Well, for starters, they're going to be very faint because they're so far away. The universe is thought to be 13.8 billion years old, which means the light from these first stars and galaxies, roughly say they've been travelling for about 13 billion years, so they're billions of light years away. So the light's been busy, diverging out, expanding all this time. So we're seeing very, very few photons off them. So they're far away, very, very faint. Also, over the last 13 billion years or so, the light, as you saw, light comes in wavelengths, sort of big. As it's busy travelling through space for the last 13 odd billion years, space-time has been expanding. This is a very sort of quite a popular diagram you often see on the internet. Here's the Big Bang, and you can see space-time has slowly been expanding over this time. So as these lights have been quietly propagating through space-time has been stretched. So you get a photon, one of these big first stars are thought to be quite massive, emitting light and ultraviolet and some visual wavelengths, sort of, yay long, but as they've been travelling along, the space in which they're travelling has been expanding, so the wavelengths are getting bigger and bigger and bigger, and that light now has been pushed out into infrared, longer infrared wavelengths. So that's why it's being stretched to the infrared. So you're probably getting where I'm heading with all of this, is that the James Webb Telescope, it's the elephant in the room, it's the man to do the job. It's much better than the Hubble for doing it, because of its mirror size, 6.5 metres versus 2.4, can collect more photons, so it can see fainter objects, and also its wavelength range. Hubble sees down to about 1.6 microns, so it just dips its toe into the near infrared, but with James Webb it can go out into the mid-infrared range length out to 25 microns. And here it is here illustrating, it can go much further out to looking at these first stars form than the Hubble could. The second thing I just want to describe is the concept of gravitational lensing. And it's a natural phenomenon, first described by Einstein in 1915 with his general theory of relativity. He said, if my theory is right, this should happen. And whereby, if you're trying to look at something really, really far away that's just too faint, but if you're lucky enough to have a large cluster of galaxies, large mass sitting between you and that distant object, that the space-time around that massive galaxy cluster, because of its sheer gravity, because of its mass and its gravity, will distort space around it and distort it into a shape like a lens effect, whereby here's your light from a distant galaxy diverging out, so things are looking fainter and fainter. The light comes up to this big lens, effective lens in the sky because of this galaxy cluster and its subsequent gravity that distorts space-time, and then you start getting convergence. All these light paths are converging back, and here we are at this end picking that up. So it's acting like a magnifying glass. So it's called gravitational lensing. So astronomers take advantage of that. You start seeing multiple and distorted and of course magnified images of that distant object or objects. And that's what this is all about. So this is James Webb's deep field view. There's a cluster out there, it's called SMACS 0723. That stands for the Southern Massive Cluster Survey. Some years ago they did a survey across the skies looking for massive clusters. They knew it was sitting out there. They chose a particular spot in the sky. How big? Pick up a grain of sand, hold it at your arm's length into the sky, that tiny, tiny little grain of sand. That's the patch of sky they looked at for 12.5-hour exposure, direct in that spot, knowing the SMACS 0723 was sitting out there in that line of sight. And SMACS, by the way, is 4.6 billion light years away. They knew it was there. They picked it up with a prior survey. So they started looking towards it and look at that beautiful view. This is from the NIRCam. Remember, NIRCam is the most sensitive instrument on James Webb. So let's have a closer look at this deep field. For starters, there is just thousands and thousands and thousands of galaxies sitting in there. First of all, identify the diffraction spikes. Get these out of your mind. Just, okay, those are just relatively close bright stars. Biff them out in your mind. Next thing you want to do is let's identify the central galaxies and the galaxy clusters. And the white round blobs in here are galaxies within SMACS 0723. In particular, this big mass up here, this is a central elliptical galaxies. Most clusters have a larger elliptical shaped galaxy at their core, and this is no different. So all these white round sort of ones here are all the galaxies contained within the SMACS supercluster. Then the next thing you start noticing all these smudges here, these distorted orange-red smudges. They are the images of galaxies. Initially they said they were up to 13.1 billion years ago. They've now refined that and they said we actually think they're possibly up to 13.6 billion years ago. In other words, 200 million years after the Big Bang. That's so speculation that of course they've got to have a closer look at it, but they're just speculating that these could be the very first galaxies containing the very first stars, these little distorted smudges here. And what they do, you might think, how are they going to get information out of that? They got computer programs, they know the simulations what amount of gravitational lensing causes what amount of distortion. So you look at the distortion, you just go backwards and you bring back your image of what the galaxies would have looked like all that time ago. So those are them. Meanwhile, look at all these other thousands of galaxies, these are just background galaxies going on here. So that was Redshift, what they call Redshift 20, or they abbreviate it called Z equals 20, and that refers to when the universe was about 200 million years old. Okay, so yeah, the importance of it. So what are the astronomers going to get from this? It makes sense. If you want to understand the whole big picture of the universe, the evolution, if you can get a glimpse of those very first stars forming, those very first galaxies, you want to know how the first stars formed, where they started, when did they first start. Those big massive stars would have gone supernova pretty early, so suddenly you'll be able to see the very first supernova explosions, the very first enrichment of the interstellar medium, for the next generation of stars. There's just a hive full of honey sitting there, just of information that's going to be crucial, essential to the understanding of the evolution of the universe, and hopefully that's, the hive that's holding the honey. So once again, what are you going to do? Whip out your spectroscope, of course. So here's NearSpec using the micro shutter array, and they picked out a selection of galaxies here. Remember, they can do up to 100 at a time. They picked out 48 individual galaxies here. And this diagram here is a series of images, is designed to show you the principle of redshift. People say, how do they know how old these galaxies are and how far away they are? At these sort of distances, they use redshift. And so here we go, and they've got the hydrogen alpha line here, which normally at sort of, say in a laboratory on Earth, what they call its rest wavelength is 0.656 microns, and which is normally over here somewhere. But everything, because these galaxies are moving away from us, the further away you are, the faster they're moving away from us. And when things move away from us, the spectrum all gets shifted more towards the red end or longer wavelengths. It's called redshifting. And I did all these figures this morning. I suddenly thought last night, because they didn't label it very well and just had to take their word that was 13.3 billion years and so on. So I started looking closely at these and got my calculator out. And I thought, well, okay, I've highlighted this here. You've got your hydrogen line here, alpha line at 2.5 microns. I kept everything in microns. So you get the difference between the two. 2.5 minus 0.656 is 1.85. Then you divide it by that base or rest wavelength again. That comes out to 2.8. So that's called a redshift factor of 2.8, or Z equals 2.8. You look it up on tables then. It involves a lot of calculations. It's not a linear thing by no means. Why? Because the universe has been expanding at different rates at different times. So I looked up on some charts, and a redshift of 2.8 gave roughly something that was 11.3 billion years ago. And there it was there. And you may not be able to see it, but there it was, 11.3. This one here, got my calculator again. You can see, once again, everything's been shifted. This is at blues and oxygen. That sits roughly at about 0.4 microns. Here's another hydrogen line. Here's your hydrogen alpha line. You're getting out to 4.2 microns now. So once again, I got my calculator out, came to roughly a redshift of about 6, which gave about 12.6 billion light years of look back time. And so it went. Z equals 8 and Z equals 9. And what they were illustrating is that further something away is from us, the longer it's been traveling, the faster it's moving away from us because of the expansion of the universe. So all these spectral lines are getting shifted more and more to the left. And once again, you just look up in the tables and they'll tell you. So NASA was quite open about that. That's the main illustration. The purpose of that slide is to illustrate how the redshift works. So I've mentioned that here. Yeah, high resolution it can do. This is the near spec, the multi-array, and spectral coverage is very wide on the near spec. NIRISS also captured the spectra of all the objects in one clean sweep. It's low resolution, but it can catch all the faint ones as well. That's the advantage of using NIRISS. You might say, why all these different spectroscopes? The other thing they're able to do then, so that was just looking at the redshift. They said, well, what are these galaxies composed of? So once again with the spectroscope, so they used the near spec once again for this and looked at all the emission lines here, and there they are, and there's oxygen, hydrogen, different energized states of hydrogen, oxygen, neon, and so on. So they're able to have a look at the chemical composition. It also gives them information how ionized things are and the temperature and the density of those ionized gases. So they're already starting to have a look at these early galaxies to just tell our eyes glancing at them are just smudges. This is the sort of information they're pulling out of them. Okay, so that's all about stars and galaxies. Let's look for some signatures of life on planets outside the solar system. This is a artist's impression of a star known as WASP 96 that they were aware of, and they were aware of a exoplanet going around it, which was labelled 96b, and Hubble had looked at it and thought, can't be sure. It may have an atmosphere, not really sure. Possibly some water vapor, unsure. It was just, they really haven't properly analysed or even discovered a proper atmosphere around an exoplanet. So out came NIRISS with its imager and its slitless spectroscope. Have a good look, and it studied it. Here's its light curve that the NIRISS imager took, and this is the light curve, the light intensity of the star, and as the planet went across it, of course, the light dipped and comes back up again. And they decided that it was 2.5 hours, 2.5 hours from here to here, so that's transferring across here. NIRISS had a look at all here. They concluded it was what they call a hot Jupiter, about 1.5 times the size of Jupiter, but only half of its mass. Obviously low density. Why? Because it's so close. It's heated up and swollen up. Has a period of 3.5 days. So it whips around its star in 3.5 Earth days. It's 1/9 the distance of Mercury is to our Sun. 1/9 of that is the orbital distance of this exoplanet around its Sun, so which is 1/20th of the distance from Earth to the Sun. So you can see why it all got hot and swelled up. So they then put the NIRISS spectroscope on it, so it's really good because it's a time-lapsing type of thing, and because it's going to be faint chemical biosignatures, so that's where once again the slitless comes in handy. And that's what the spectroscope in the near-infrared from the NIRISS instrument, and that ties in beautifully consistent with water vapor. And it's not surprising, something that hot is going to be steam going away. So it just really showcases its ability for look for biosignatures. Miri will come into play with future exoplanets, looking for methane, further water. Oxygen is a sign, obviously, of life on a planet. Methane, possibly. You start seeing things like CFCs, fluorocarbons, and so on in the atmosphere. You know that those people are like us. They're very good at stuffing up their atmospheres and screwing themselves up in the future. So they're pretty up there with humans, really. That's what we're good at doing. But of course, they might see industrial pollutants and all sorts of biosignatures of activity that's going on the planet. So that's what they hope to do with that. Okay, so wrapping up, in a nutshell, design features and operational capabilities. We've got a large primary mirror, which makes it extremely powerful, enables it to see faint, small and distant objects at high resolution. Its location, 1.5 million kilometres away from the Earth and away from the Sun, plus its sun shield, its gold-coated mirror, specialised detectors, cryogenics, all those design features allow it to see really in a very, very sensitive manner in infrared wavelengths. It can see objects at extreme distances, the first stars and galaxies, all these early protostars and shrouded in dust, protoplanetary disks. It can see dust and emissions in those mid-infrared where dust gets heated up. The atmosphere around exoplanets to see if there's signs of life or other things going on, stars dying and so on. And that's why the James Webb Telescope is an extremely powerful infrared telescope providing a gateway to a golden era in astronomy. Thank you. Now, there's a lot of technical stuff more that I didn't go into, because some of it's a bit over my head, or having gone through it, it's a lot of it's sort of very technical. There's a lot of other interesting material, papers that I've got and stuff. So if anyone's interested, either online, you want a handout. Everyone here today's had a 2-page handout. So if you're online, you want a handout, summary, or I've got some 2 excellent technical papers for the general public, technical ones from NASA. And I've just got some other really good stuff, resources at home on PDF files. You're welcome to send me an email. Any of you guys here, any of you guys on YouTube, membership@astronomy.org, and I'll be more than happy of sending them to you, because it's a lot of fun pulling it all together, and it's just neat sharing. But any questions, first of all, Life? Yes, yeah.
You know, in one of the first images, you showed, the Earth orbiting around the Sun. And then you kind of put the space telescope like it had an orbit like of its own.
Oh, yes, an L2, yes. Oh, I know the picture you mean, yes.
That's what the L means.
The Lagrange point, yes, L2.
Yeah, they can have an orbit of its own.
Yes, it does. Yeah, good question. Yes, yeah, good question. So probably what you're asking is, hey, when it's out at L2, does it just sit there and move along, or is it, in the diagram it had this nice little orbit. And you're right, absolutely right. It doesn't just sit there like this and follow them around. It has its own orbit. For 2 reasons. It can look at different angles at objects that it wants to look at, but also it's got solar panels. So it's primarily powered with solar, and it doesn't want to sit in the shade of the sun and the Earth, so it wants to spend a bit of time outside from there. But still protected with the sunshade, of course.
So does it actually orbit the sun? Or?
No, it orbits that point L2, which goes in conjunction with the Earth as it orbits the sun. So indirectly it's orbiting the sun. Sun here, Earth here, L2. Earth and L2 are orbiting the sun. L2 point, the telescope is going around in about a 6-monthly orbit around that L2 point as it goes. So sun, Earth, L2, and James Webb doing that. How does it do that? About every 3, it's got a little bit of hydrazine, it's a hypergolic fluid, bit of hydrazine in it that it uses to burn, just to change its orbit, just to keep it in check. Doesn't use much fuel at all. But you're right, it doesn't just sit there, it's on the move in a little circular orbit around L2, which in turn orbits the sun with Earth.
So does it actually go around the Earth?
No, it does not go around the Earth. It doesn't go around the Earth. Correct.
It orbits around the sun, but it stays connected to the Earth.
Yeah, gravitationally connected is a way to put it. Yeah.
So is that sort of like a tidal rocket? Is it a similar phenomenon? Not really.
Not really.
No.
It's a balance between the gravitational, and I've got very diagrams. It gets a bit complex, but it's just gravitational with a balance of, because you're a little bit further out. Sort of, everything's, when everything's going around, you've got angular momentum going on, and just that particular distance, it's just held there. It's in a point. A good way of putting it is a gravity well, and it's on a ridge. You see a gravity well of Earth, gravity well of the sun. It's another way of looking at it. It sits on a little ridge there. It's not getting sucked in towards the Earth, and just the force, and that point gets dragged around with the Earth around the sun, and those little Lagrange points remain nice, stable little ridges. And it is a little bit complex. Obviously, the guy was a clever guy who worked it out and predicted it all. But yeah. Yep. Yeah, Robert.
Does it have a visible light spectrum camera on as well, does it?
So does it have, a light?
Visible light camera.
No, it's all infrared.
So it's a false colour.
Oh, those are all false colours. Yeah, how they do, when they look at something, they put on filters, so they just see things in set wavelengths. And they take an image in one small range, with a filter on. They take another image, And each of those images, everything in electronics is, computers, is off or on, 0 or plus. So it's all in sort of black and white, a little bit of grayscale going on for intensity, but it's essentially in black and white. They then get, say, 3 or 4 images of one thing, all different wavelengths, and they allocate a colour to that wave, to a particular wavelength, to try and make some sense out of it all. Because at the end, what is colour? Colour is just a property of light being reflected or emitted from an object that our retina and our eyes receive, detect, and then our brain interprets. We've only got 3. They're picked up by cones in our retina. We've only got 3, green, blue, and red, and then our brain mixes the combination together. So they try and match that up to help you visualise it. Visualise it for 2 reasons. One is to make pretty pictures to keep the taxpayer happy who's paying for all of this. And the second thing is, even as an astronomer, they look at it and it just gives, we're visual creatures. We love stories, we love visual, we love pictures. So it helps them understand things. They go into a bit more depth than that and looking at narrowing down their wavelengths and a bit more focused. But they do a similar principle. They'll often look at something that's been colorized. But primarily it's colorized to look pretty.
So the spectrograph also works outside of that, doesn't it?
Yes, spectrographs are in black and white. And they get colorized, so they look nice. Yeah, but even spectrographs are in black and white. Yeah. Yeah.
The engineering question: what sort of materials do they use to actually run the to actually build the cryogenics to actually sustain that temperature for that period of time? Things become brittle at certain temperatures, that sort of thing. So how do you get the durability?
Good question.
At that temperature?
You're one I best send that technical paper to you. But the mirror is made of beryllium, and I wouldn't be surprised if some other parts of beryllium. Well, beryllium is good because it's very light, because you want something light to be up there. But beryllium is very rigid against the extreme temperatures of space, in particular the frigid temperatures. So look, directly to answer, what is the material that the cryogenics system is made of? I don't know. It'll be in that paper, and I'll flick you an email with that paper in it. But I wouldn't be surprised there's some beryllium in the mix there, because I know beryllium is used for the mirror because its rigidity in frigid conditions, and it's nice and lightweight. So I wouldn't be surprised if it is that, but the honest answer, I don't know. But I can flick that technical paper to you. Good question. Got any questions?
One from YouTube.
Oh, yep.
This is from Jonathan Park.
Oh, Jonathan, yeah.
He says, very enjoyable talk, amazing images. Can you tell us how they decide which of the 4 spectroscopes to use?
Yeah, good question, Jonathan. Yes, there's 4. There's 4 spectroscopes. It's like one big spectroscope in the skies, and there's 4 spectroscopes up there. You've got the NIRCam one, the wide field slitless. You've got the multi-object spectroscope on NIRSpec. You've got NIRIS has got its slitless spectroscope, and MIRI's got its spectroscope that can operate in slit or slitless mode. So you've got 4 up there. How do you decide which one's going to use? It depends on what you're looking at and what sort of information that you're after. For example, and there's various factors you want to take into consideration, like everything in life, it's a trade-off. And those probably the 4 factors that I identify would be, how faint is your object? If it's really faint, you want to get as much light as possible, you're going to go slitless. If it's really bright, but you want high resolution, you're going to go for example, the NIRSpec or MIRI, if it's infrared. So how faint an object is, your field of view varies with each instrument. So your field of view, as mentioned, your spectral resolution, what you're after with it, or what you can get away with it. And the other one, as I've alluded to, is your wavelength coverage. So those 4 factors there, Jonathan, are the main factors that you're gonna play as a bit of a trade-off with what one you're going to choose to do the job. I think otherwise we're all good. So thank you everyone for your attention. Get a little late, and thanks for coming out once again. Drive home safely and have fun. Thank you. Right, we can relax.